right, we are recording. Okay, so we pick up where limits left off and we start moving into the concept of the derivative. And the derivative comes from what last unit we called Formula 2. So recall Formula 2. And there it is right there. There's Formula 2. And Formula 2, the other thing I want you to recall about it is that we had a couple of questions where you'll remember that we used Formula 2 to find a general equation for the slope of some functions. And when we wrote the test at the end of last week, some people were even saying, how come there wasn't a general equation question? I studied those so hard. Well, don't worry. But that effort will not be in vain, because that's a big idea in this unit. In fact, it's kind of the only idea in this unit. Remember that when we say a limit as h approaches 0 of this formula, remember that at the end of the day, this m, of course, remember, stands for slope, right? And the whole point of all of this was that if you have some sort of curve, and we'll call that point there the x-coordinate a, which means, of course, that it has a y-coordinate of f of a. And if we want to know the slope at a point, let's say I want to know the slope at this point up here, I basically shrink the distance between them, right? The distance between here and here is called h. So this is a plus h. And this would be then a plus h comma f of a plus h. And then we had, of course, two different formula ways that we could look at finding the slope as this distance from this point to this point got smaller and smaller. We could do it as a shrinking secant line, which was, I guess, Formula 1, I suppose. And then we did it as a rise over run, which is where we got Formula 2, right? Because run is just this h. But now I want us to kind of think back to what we did in last unit, where we, again, found a general equation for some functions. What if we looked for a general equation for every function? So the derivative of function, any function f, so again, so say this is the function f of x. The derivative of function f at the number where x is a is, and you got to write small here. They didn't give me much room, so I'm going to write kind of smaller. Hopefully you can see this. Is the value f primed of a. So I'm going to start using prime for meaning the slope. So I'll even say aka. Also, everybody knows that ak means also known as the slope of function f at the point where x is equal to a. But suppose we let a vary. And we'll pick it up right there after O Canada. I'll just pause here for a second. And there we go, we're live again. There. Suppose we let point A be anywhere along the curve. We let it vary. We don't, pretty much, except for those general questions that we had, those couple of general equation questions we had, we've always kind of had a value for A. But what if we don't define A, we just let it stay in X? So suppose we let A vary. You know what, I didn't mean to finish that sentence at that point. Let me erase that. Suppose we let A vary over the domain of function x. Then, instead of a in the formula above, we have just an x. But we're going to now call this thing f primed of x. So f primed of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. And I know that doesn't look terrifically different from Formula 2. It isn't. Except that we're not going to specify an a value. We're going to leave it as an x. And we're going to call this thing the derivative of function f. That up a bit. So basically, the derivative of a function at a point is the slope of the tangent line at that certain point. So for example 1, let's think about a function like f of x equals x squared, just a good old easy to think about parabola. Let's find f primed of x and then determine f primed of 3. So f primed of x, again, which is just called the derivative of x, is the limit as h approaches 0 of f of x plus h minus f of x all over h. So think about what that formula means. That means I want the limit as h approaches 0. F of x plus h means plug in x plus h where the x is. So the equation is x squared. So I have x plus h squared minus f of x. So that's just going to be minus x squared all over h. All right, what's that going to be? Well, let's expand that bracket and see what happens. Right now, I have the same problem we've always had with these things. I can't plug a 0 in for h without having to be stuck trying to divide by a 0, and I can't do that. So I'm going to expand the bracket. That's going to give me x squared plus 2xh plus h squared. And as you can see, that's actually going to work out pretty well. The x squareds will end up canceling, and I end up with a numerator that has nothing but terms that have an h factor. So I can factor out the h, leaving me just 2x plus h in the bracket. And now that it's a factor, I can divide. And I now have the limits as h approaches 0 of 2x plus h. All right, well that's not gonna be divided by 0 if I plug in the h now. Okay, and there we go. So this is the derivative f primed of x is equal to 2x. So in other words, this is the equation that represents the slope everywhere along f of x. Now remember that f of x was a parabola, right? It's x squared. Think about what a parabola looks like. How can the slope everywhere along a parabola be an equation like 2x? What kind of an equation is 2x? It's linear, right? It doesn't have an exponent on the x. Well, it does. It has a 1. Right? Y equals 2x is a straight line with a y-intercept of 0 and a slope of 2. How can that be? Okay, we actually didn't finish the example. Let's finish the example first. We do want to find out what f primed of 3 is. So, of course, that's just going to be 2 times 3, right? Because f primed of x is 2x. So f primed of 3 is 6. So again, what does that mean? That means at x equals 3, f of x, which equals x squared, has a slope of 6. And there's a name for what we just did. This is called the method of first principles. And what we mean by that is, we mean that the very first principle we learned about what the slope of a curve is that it's a limit. What does that mean? Well, it means that we were kind of thinking about turning secant lines into tangent lines by putting the points closer and closer together. So that's kind of the very first principle of derivatives. Is this the way we're going to keep doing derivatives? No. Starting a couple classes from now, we're going to have a completely different way to do it. But for right now, this is the way we're doing it, and this is the way we got to practice it, because it is expected that any calculus student understands the first principles, right? Just like we expect any student in grade 8 to be able to pick up a calculator and long divide big numbers in the calculator. Well, that's because back in grade 5 and 6, we did show them what long division actually is. I mean, they should be able to do it the old way too, right? So we will replace this method with something a little more efficient, but not for a couple days yet. Okay, so let's think about this visually. I think the next page is a graph, right? Okay, let's compare the graphs. So the first graph we'll look at just what f of x is. So f of x will be on this graph. And okay, what was f of x again? Oh yeah, f of x was the function x squared, a parabola that you've drawn many, many times. It goes through 0, 0, it goes through 1, 1, it goes through 2, 4, it goes through 3, 9. And of course, when you square negatives, you get the same thing. So it's got symmetry across the y-axis. So there we go. There's our old friend, y equals x squared. Whoops. Oh, I don't like that line. Let me try that again. Ta-da. There it is. All right. Now, I'm going to have to shrink this so we can see both graphs at the same time. So hopefully you can kind of see this. We should have put them next to each other. There we go. Okay, what I want you to do is I want you to think about the following. Think about how the slope of f of x is changing as, let's say, you go from a domain of negative infinity to infinity. So as you start way over on the left, what kind of slopes do the lines have? Here, I'll use a highlighter. I'll use yellow first. What kind of slopes do we have as we go around the curve this way? Think about every single line that would make a tangent on here. Here, let me use a different color for the tangents. Ooh, can I make a yellow line? I don't know. I've never tried that. More colors. Oh, let's see. Ooh, let's make a yellow line. Let's see. What's that looking to look like? Oh, that didn't work. Oh, well, anyway. Like right there. What kind of a slope do I have there? I don't know. It's like it has about a rise of -1, 2, and then a run of 1. So I don't know, maybe that's a slope of about -2 or -3 or something. But now think about the slope as I go further down this way. Definitely that's less of a slope. In other words, the further to the left I go, the more negative the slope is, because it's a steeper downward line. But the closer I get to the vertex, the flatter the slope is. So it's pretty easy to see that if I was making a graph that represented the slope as it changes, so this is going to be my line that represents the change in slope as I go around the curve. Well, it's actually, we already know that f prime of x is actually equal to 2x. And I'm going to say again, I wanted to make this yellow. Can I write in yellow? Let's see. Let's try this. I'm going to say that the slopes, oh, that's still not working. I guess it won't let me write in yellow. So the slopes of tangents as x is less than 0 are negative and decreasing, right? Remember that when it comes to negative numbers, negative 10 is smaller than negative 1, and negative 100 is smaller than negative 10. So I'm decreasing as I go left. So here, I want this in yellow, so I'll just use the highlighter. Yellow, 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 yellow. So see the part of the graph that I highlighted yellow? I guess I could get rid of all these extra tangent lines. I don't know if they're that useful. So all the parts there that I highlighted yellow are kind of down here. Now let's actually graph this line. Okay, how do you graph y equals 2x? Well, it has a y-intercept of 0 and a slope of 2. So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. Down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1. So there we go. So there's the line. And the part that I highlighted yellow on this graph is right here, right? Okay, now you can, hopefully you have a little bit of room underneath. I'm kind of out of room, so I'm just going to write to the right here. How about the tangent at x equals 0? What is the tangent line at the vertex of f of x? So let's draw that. Here, I'll do it in this lovely purple. Well, there it is right there, right? Right? It has a slope of 0 because the tangent line is horizontal. Horizontal lines have a slope of 0. Think about why that is. Why does a horizontal line have a slope of 0? Oh, yeah, because slope is rise over run. So between any 2 points, how much does it rise? 0. 0 divided by anything is still 0. So this purple line here has a slope of 0, and that makes sense because take a look. My function at x equals 0 for the slope is 0. And then lastly, I'm going to say, here I'll use blue for this, the slopes of tangents where x is greater than 0 are positive and increasing. We actually did find one of them in this example, right? We found out that the slope when x is 3 was 6, right? So if we were to rise 1, 2, 3, 4, 5, 6, and run 1, we'd get some sort of line, really steep line like that. That has a slope of 6. What happens if I move that point further up, though? Oh, the slope would become 10, 11, 12. It gets steeper and steeper the higher I go. The lower I go, it's still positive, but of course, it's shrinking. That's why this line looks like this. Let's see, let me use blue so that I can kind of keep the color scheme going here. Right? The slopes of tangents where x is greater than 0 are positive and increasing. And I can conclude the slope function for a quadratic is linear. Let's see if that's true on the next one. Let's see if we can prove that that's the case with another example. Okay, I can get bigger again. I don't need to go sideways. So for example 2, let h of x equal 3x squared plus 4x minus 5. And I want an equation for the slope everywhere around that quadratic, around that parabola. So h primed of x is equal to the limit as h approaches 0 of, I guess we could say h of x plus h. H is kind of an unfortunate letter to use. Minus h of x all over h. So let's plug that in. So that's the limit as h approaches 0 of, remember this h doesn't represent a variable, it represents the function name, which is kind of a silly thing to name it, but all right. So I'm replacing the x in this function with x plus h. So 3 times x plus h squared plus, instead of 4x, I say 4 times x plus h minus 5. Then I just subtract the function. But careful, I'm subtracting the whole function, right? So put it in a bracket so that you don't forget that you're subtracting all of it. Right? You learned the distributive property of algebra in grade 8. Let's not make grade 8 mistakes in our work, shall we? All right, let's see what that's going to look like. That's the limit as h approaches 0 of, okay, I'm going to have to expand this thing. So I'm going to expand the bracket here first. This bracket right here, I'm going to expand. So that's going to be 3x squared plus 6xh plus 3h squared. I kind of did two steps at once there, right? I squared x plus h, and then I times all of its terms by 3. Plus, let's do this part now. So that part there is right here. Now let's do this part. What's that going to look like algebraically? Well, it's just going to look like 4x plus 4h. Oh, and then of course there's a minus 5. Don't lose him. Then this part here, let's do this part in a different color. Let's use pink. That's a nice color. This part here is going to be over here. Oh, I guess I forgot to highlight this part. Okay, so now let's put that part there. So that's going to be go back to the pen. There we go. Minus 3x squared minus 4x plus 5 all over h. Does everybody see where those parts came from? Okay, actually, I kind of find those in the way. I'm going to get rid of them now. Oops, got rid of my divide line too. There we go. Let's get rid of that. There we go. There we go. Oop. Come on, get rid of just the purple part. Jeez. Oops. And then I goofed it up. That should be a mine. Oops. Ah. There we go. There. Okay, let's collect all the like terms. Notice that 3x squared and 3x squared cancel. Notice the, oh, hang on. I just realized this should be a plus, shouldn't it? Minus 5 and plus 5 canceled. And let's see, anything else? Oh yeah, plus 4x minus 4x. Looks like we have good news. Every term that's left behind here has an h for a factor. So I can factor it out. And then I can divide h by h. And I now have the limit as h approaches 0 of 6x plus 3h plus 4. All right, I can plug in the 0 now for the h value and get 6x plus 3 times 0 plus 4, which is the linear equation 6x plus 4. So that's it. H primed of x, the equation of the slope everywhere around the parabola h of x, is linear, which is what we concluded after example 1. Okay, there's a B part to this question, I think. At what point on h of x does the tangent line have a slope of 10? Well, remember, that's this thing. That's the slope. So I just go, well, if h primed of x is equal to 6x plus 4, oops, I don't know why I put a bracket there. I don't want that one. Oops, come on, you. There we go. Then I can conclude that 10 must equal 6x plus 4, and then minus 4 from both sides. and divide both sides by 6. Therefore, at the point where x is 1, the slope of h of x is equal to 10. And it did say at what point, so I should probably go back and figure out what the y coordinate is. So let's see, if the x coordinate is 1, go back to the original equation. What was the original equation again? It was 3x squared plus 4x minus 5. So let's see, h of 1 is 3x squared plus 4x minus 5, which is, let's see, that's 3 plus 4 minus 5. 7 minus 5 is 2. So I should then say, for my conclusion, at the point, and what was the point again here? 1, 2. All right, let's use Desmos and verify that. So let's have a look. I'm going to open up, you know what, I haven't opened up Desmos yet today. Oh, hang on, I want to update that. Okay, Desmos, there we go. Excuse me. Come on, Desmos. Maybe I should get out of tablet mode, that might help. There we go. So, okay, so let's graph. Let's graph. There we go. H of x is equal to 3x squared plus 4x minus 5. There it is. And we think that at the point, let's call it, we don't have to call it anything. We think that at the point 1, 2, that we should have a slope of 6x plus 4. Okay, so let's see. Or we think we should have a slope of 10. Sorry, at the point 1, 2, we should have a slope of 10. So first of all, let's graph the line y equals 6x plus 4. And notice that, let me shrink that a little bit. Notice that that's kind of showing us that that as we graph this thing, right here is where the slope ceases to be negative and begins being positive, which of course is right above it, right there, right? The green line ceases to be negative, begins to be positive. Now, how do we check to see if we have this right? We think the slope at this point should be 10. Well, let's make up an equation, right? Use y minus 2 equals the slope of 10 times x minus 1, right? I'm just making an equation, and look at that. That looks pretty good. Here, let me just hide the slope line for a second. That looks pretty good. It definitely looks like it touches at a tangent right there. If I zoom in, I can see a gap there in the space. I can see a gap there. I can see a gap there. It looks like we have a good tangent line there. And let me just go back and zoom out again. I should also point out to you that actually Desmos can calculate derivatives for you. You can just enter in, I would like the y line to actually be the derivative of this function h of x. So I actually type it in the way that you just saw me write it down on the lesson. H primed of x. And let's see, oh, hang on a sec. That didn't work, did it? H primed of x should be, oh yeah, it did. Sorry, get that out of the way. Where did we say that the slope everywhere was represented by the line 6x plus 4? And there it is. Black line, green line, black line, green line. So there we go. So that's our quick introduction to what a derivative is. It's the function of the slope everywhere. What we called last chapter the general form of a slope equation, of a limit. Okay? So, let me stop my lesson recording.